Hello and welcome to week 2 of Techniques in Analytical Chemistry. I'm recording this meeting because I have to go to a surgery consult on Tuesday. So I won't be able to, I wasn't able to make the actual meeting time, and I got permission from the higher ups to pre-record the meeting so that we could still have the lecture. And then I'll post this video for you guys, and then you always won't have to come to lecture on Tuesday. And I'll also open up the quiz for this week. We have our first quiz this week based on last week's material. All right, so I'll post it. It'll be online. And of course, if there's any problems, we can always, revisit it as we go along. Okay. So where are we? Okay. So let's go back here. All right, so I managed to post the schedule as well. So let me zoom in on it for you. Full screen this. Want to zoom in? No, okay. All right, so here is the schedule that I posted. Share that. Can you share that? Yeah. Let me share the screen. That'll make it easier. Okay, so hopefully you guys can see that. Yeah, so if you look at it, we've posted it so that it matches the lab, so that Amanda, your lab professor, she emailed me and asked me to check if the schedule for the lab will follow the schedule for lecture. And so, you know what, it looks like the way that Tudor, the professor used to run this course last year, it looks like it was laid out pretty nicely already in this nice order. So I think we're already good. But I'm going to just go through the lecture schedule, and we'll run it based on this schedule so that the lab modules match. All right. So if you guys notice, we're in week 2, September 9 to 13. You see we have elution order, normal phase chromatography will be what we cover in the actual lecture. And you guys will have quiz 1 based on last week. I'm good to follow this quiz schedule, although the midterm is going to be on the first actual test is going to be on the day after Thanksgiving, the 15th. So I'm not sure if the schedule matches. Let's see. No, it doesn't. So yeah, it's going to be on the week of the 7th. Week 7, October 14th to 18th will be our test. So I'll make sure I edit that for you guys. I can even do that right now if you want. So it's going to be test 1 will be on October 15th. Test 1, October 15th. All right, and then I'll make sure I cross it out so that it's not the same here. Alrighty, but I'm still happy to follow the rest of the schedule. Okay, so I'm going to save that as the fall 2024 schedule. If it will decide to work for me. Oh, whoops, it thinks I'm going to put it on the actual printer. There we go. So this is going to be the fall 2024 schedule for techniques in analytical chemistry. Okay, and I'll repost that as we go. So anyways, where are we? So schedule, lecture 1, lecture 2. You guys will do experiment 1, 1, 2, and then 1, 3, a 3-week lab, it looks like. And then you guys will start, we'll try to follow that sort of lecture batches, the schedule. Now, I'm seeing that it says no lecture week 5. I'm going to confirm what this means because I'm not really sure why a test would make sure that we have no. Like why another test would interfere with our lecture. So I'm going to confirm what that means. So I'm not really sure. I haven't seen that before. Yeah, another midterm test says there's no lecture that week. So I'm gonna check because a lot of this is looking kind of fuzzy. I'm not really sure why we would have, because you guys have another test, we'd have no lecture. Maybe it's during the time of our test. I have to confirm with Amanda. Alrighty. Anyways, so let's get to the elution order in normal phase chromatographies. I believe, yes, that's where we want to be. Beautiful. And also, this is good for a pre-recording because because yes, I understand. Because the lecture itself is actually pretty short, so it's not too bad. Okay, here we go. So elution order in normal phase chromatography. All right, so last time we talked about describing our chromatographic setup in terms of stationary phase and mobile phase. I don't know if I can make this smaller. This thing's kind of in the way. Let's go up here. There we go. The separation of components by chromatography as resulting from differential retention onto the stationary phase. Right, so they will separate because they attach to the stationary phase in different ways. So we talked about describing the role of polarity in modulating the retention of analytes in chromatography. That's specifically for a column that uses polarity as its separating, factor. Measuring the void volume of a column for system suitability assessment. Normal phase and reverse phase stationary phases, right? That's the silica gel on the column. And then making appropriate adjustments if necessary to speed up or slow down your elution of analytes in normal phase and reversed phase chromatography. So remember, what's the role of polarity in liquid chromatography? And again, this is only if the stationary phase is based on polarity. So if our stationary phase has a non-polar polarity, right, then that would be a reverse phase chromatography, right? That means our mobile phase should be polar, right? And that means our elution order in reverse phase will be the most polar first. And if we increase the polarity of the mobile phase, in reverse phase, we will increase the retention time of our products, our analytes. And normal phase, we have a polar stationary phase. If our mobile phase will tend to be slightly non-polar. The elution order will be non-polar first. And if we increase the mobile phase polarity, we make it more aqueous, right? We will reduce our retention time. Things will come off the column faster. So in this presentation, we're going to talk about describing the intermolecular forces that are responsible for the retention of analytes in chromatography, with particular attention to normal phase chromatography. We will correlate the polarity of an analyte with its molecular structure. So we'll be talking about those functional units that we talked about before. You guys are taking organic this semester, so that'll get more clear as the semester goes on. We're going to predict the elution order of analytes based on features of their molecular structure. And we'll explain the need of applying mobile phase polarity gradients in chromatographic separations. Okay. So retention of analytes to the stationary phase. Remember, this is a polar phase in normal phase. The polar stationary phase can have dipolar interactions. That means positive and negative interactions, right? And hydrogen bonding, right? Positive hydrogen to negative oxygen, vice versa. We have van der Waals forces. Those are the weakest ones. In weakest interactions, kind of non-specific between different molecules. We have partition between two solvent phases, right? So if you have a dissolution between two phases, they might, at the mixture point, they might absorb on the stationary phase. Ooh. So there's a little asterisk here. You have a partition between two solvent phases, which is the polar layer immobilized on silica or on paper in normal phase chromatography. I'm not sure what they mean by fundamental to the bonded phase of reverse case. We'll have to check that out and see what that means further. All right, team. Okay, so normal phase. So we have our, I don't know why we're going into this more. Is this just like another question? So the partition or dissolution between two solvent phases, you can have the mobile phase and the solvent absorbed on the stationary phase. So this is a picture that Tudor must have drawn. Oh, so this is just a picture here. So um okay, so if you look at this, they have octane and water as two mobile phases. There's a partition in between, right? We have silica gel and we have water molecules here. The analyte may be traveling through the column, right? But honestly, you know what? This picture is kind of hard to interpret here. I'm gonna try and interpret that further, and we'll go from there. Let's just keep going, and we'll come back to that. So so a molecule is polar, right? If it has electrical charges or dipoles, or if it is able to undergo hydrogen bonding. So water is a very polar molecule. I don't know if I'd call it the most polar molecule, but it's very polar. So what drives the polarity in water is the presence of oxygen, which has a high electronegativity compared to hydrogen. It also has some lone pairs, but the electron density of water will tend to be more concentrated around the oxygen, meaning you'll get a negative charge closer to the oxygen. If the electrons are pulled away from the hydrogen, you'll tend to get, excuse me, if the hydrogens have their electrons pulled away by the oxygen, you tend to have a more positive charge around the hydrogens. And so what you'll see happening is you'll get these bonds between the positive water, or the positive, excuse me, hydrogen portion, and the oxygen in the molecules around themselves. And it's a pretty powerful bond. That's how DNA bonds together through the middle of the helix. It's also what gives water its really intense surface tension compared to other molecules. It's hydrogen bonding. So as you can see, water has a dipole as well as the ability to hydrogen bond. So it's got double, the ability to be polar. So how do we predict polarity based on their molecular formula? So you can predict the polarity by counting the number of oxygen and nitrogens. These are very good for hydrogen bonding. Between different parts of the molecule. You have a positive, you have a negative portion of the molecule, right? So let's look at the example here. We have beta carotene, a long hydrocarbon chain. Now, if you guys aren't too familiar with organic just yet, every intersection of the skeletal chain is supposed to be a carbon. Any functional groups will be listed as their, within clear writing without any without just being a point there. But you can put CH3 groups as just a stick. And if you understand organic, you should be able to understand what you're looking at. Any double line that's a double bond, single line is a single bond. And so let's see here. We got beta carotene, right? And so we look at it, we don't have any oxygen or nitrogen molecules, right? So we can probably assume that it's not too polar, right? Especially since it looks very symmetrical as well. If you notice, molecules that tend to be very symmetrical, right, tend to have a less polar, what's the word I'm looking for? They tend to be less polar. Because any charges that are on one side tend to be balanced out by charges on the other side. So you don't get a massive difference in charge across the molecule because it's symmetrical. But as soon as we put in and again, it's still going to have its own polarity, right? As soon as we throw in an oxygen, it's going to, and because it's not perfectly symmetrical, you have one further on top, one further on the bottom. It's mirrored, but mirrored in two dimensions, right? So it's mirrored once across the mirrored once, if I can draw here, mirrored once this way, but also mirrored this way, right? Then you're going to get a buildup of charge on one side, so negative up here, which won't be balanced perfectly by a negative over here. So the negative will be at the bottom, so you'll tend to get a side of the molecule that is more negative and one that is more positive. And so this makes it more polar because it's able to do those hydrogen bonds. So for a normal phase column, we first expect the most non-polar molecule to come off first, right? So let's look at this. So no charges, no hydrogen bonding potential from the beta carotene, right? So it has no affinity to the polar stationary phase, right? It's like uh, dissolves like, right? It's not like opposites attract in this case. This is a like dissolves like situation, right? So the non-polar beta carotene will pass through the column because it has no affinity to the polar stationary phase. Now, this might not be, absolutely true. There might be some van der Waals forces, right? So a little bit of shifting of electron density, which can give things a little bit of a charge, which can then give it a little bit of polarity, right? But it's very negligible, right? So if you were going to use a molecule like this, you could probably call this your void volume, as this one comes off first. And then you look at your xanthophyll, because it has those the extra oxygen atoms, it will be retained on the column for at least a little bit because of its ability to form hydrogen bonds and be polar. So here we have an alumina stationary phase. So this is just a alumina silica stationary phase. So it looks like it has the ability, again, Al2O3, where are we? Yes. So alumina is your stationary phase, right? And you can notice it's got a nice positive charge, right? So I guess this is just an example of something that could be a good stationary phase for normal phase chromatography, right? So here we have, I guess it's just showing you the interactions between different molecules. So you'll notice it's able to, form those hydrogen bonds between this molecule here, which has a carbonyl group, a acetyl bond to an oxygen. It's also showing that it's able to bond to, it's hard to tell which one we're specifically bonded to. This picture is really unclear. And also, you guys will notice once you are good in organic chemistry, anytime you see an R group, that's just referring to a carbon chain of some kind. So R group, it could be any carbon chain attached to this carbonyl group at the end here. And usually if the R's are the same, then it's the same group they're talking about. So you look at this one, looks like this is not a ester. I'm not sure anyways, but the R group, again, the R group is just a chain of molecules. Same thing here. This is a carboxylic acid, right? So yes, the rule is, and again, don't worry exactly about what the stationary phase is. Worry about the polarity of the stationary phase. All right. Worry about its polar. Don't worry about exactly what it is. The silica gel columns we use, they have very complex structures. I don't think we're ever going to require you to understand exactly what they're made of. Just understand the principles involved. So yes, the rule is the more polar it is, the stronger the bond to the alumina is. So solvents in order of increasing polarity. And this would be what you would use to help get things off of a column. So you would mix these things together in certain ratios, right? And you would, by experimentation and having a standard, what's the word I'm looking for? The standard operating procedure, they will have figured out what the good ratio is for your particular column. You're usually going to be told what it is, but through some quick experimentation, you can usually figure out what column gives you a decent void volume, or what solvent, I mean, and what combination will give you good separation between your peaks. You don't want them to all come off at once. You don't want it to take 45 minutes for each one to separate, right? You want like 1 or 2 minutes between each one coming off, or 1 or 2 milliliters if it's a normal phase column. You want it to be, relatively fast, not take forever, but also not come off at once. So here's a list of solvents of increasing polarity. So petroleum ether, and again, I'm not sure why we would say petroleum ether is low polarity because the word ether gives me a polar vibe. I'm gonna have to look up look up the actual formula. Petroleum ether. Ether. C6H14. Oh, okay. So that's because an ether usually has oxygen in it. So that's what I was confused about. So there's petroleum ether. Okay, that's fine. So if you notice, petroleum ether has an oxygen in there, right? So I guess if this is what we're looking at, any kind of petroleum ether has a single bonded oxygen in the middle of the chain. If it's more symmetrical, then it will be less polar, right? But if the chains are different sizes, the polarity will increase. Anyways, so increasing polarity, hexane would be your, again, I don't have my ability to draw right now, but hexane would be, and as a straight chain, a hexane would be your 1, 2, 3, 4, 5, 6, a chain, carbon tetrachloride, so CCl4, Cl coming off of everyone, Cl, 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 Cl. I get my ugly writing, I'm sorry. So carbon tetrachloride, again, very symmetrical molecules, low polarity. Benzene, benzene being your, oh man, this is such a bad drawing. Benzene being a cyclohexane with 3 double bonds. I need to get my tablet so I can draw on these things. Chloroform, methylene chloride, diethyl ether, ethyl acetate, acetone, pyridine, ethanol, methanol, water, and acetic acid. So and again, you would use these things based on safety as well, right? So you're not going to just jump to the next one on the list. If you have access to like ethanol or water, right, and maybe some hexanes, yeah, you're probably good for any ratio you could possibly want, right? You would just mix it up and try to figure things out and see what gives you the best ratio, right? You can also Google good ratios and stuff like that, right? It's all been done a million times. You can probably get a good ratio in your solvent. So this is a popular range. I'm not sure what they mean by popular range. So the second criterion is the miscibility of its solvent with its neighbor. So miscibility is important because you want to make sure that your chemicals will mix together and form a solution when you mix them together so that you won't get weird borders between like little bubbles of each solvent. You want it to all be uniform so everything comes off evenly, right? If they don't mix like water and oil, oil would be very nonpolar, right? Water is very polar, they don't mix, right? But water and methanol or water and ethanol or water and chloroform would be very miscible. So yes, it is necessary because you want things with widely different polarities to be able to mix together, right? Yes. So the miscibility will allow you to get the more tightly bound analytes off easier. Okay, so in reverse phase chromatography, your aqueous phase will be your polar component of the mobile phase. The organic phase will be your non-polar component of the mobile phase. And again, we're just reversing what we're looking for, right? Yeah, we want our solvents, right, to increase in polarity to remove things off of the column faster, right? When it's normal phase, and the opposite for reverse phase. So methanol, and which is something I didn't know before, methanol is polar for normal phase chromatography, but counts as non-polar in our reverse phase chromatography. Now, methanol, I'm not sure why it counts as non-polar for reverse phase. I'll probably have to explore that further as well. So If you have a unique composition of your mobile phase, you will call this an isocratic elution. If we have a gradient, so isocratic being basically uniform, and this is the simplest way to have it done. Um, as you gradient things, you will increase the complexity of things. And if you want to do multiple runs, you have to make sure the conditions are exactly the same. So what you might find in HPLC is they would have, if they had a gradient, it's computer controlled and very, very similar each time. So you can, compare your results to your standards, right? I would say isocratic is much easier to do manually. I don't know if it's even possible to do gradient properly manually. But yes, if your composition changes during the run, we call this a gradient solution. So if we either lower the polarity, right, over time, as in reverse phase, or we increase the polarity over time in normal phase, then we are, having a gradient solution. So this is in order to remove very stubborn analytes from the column, and also to make sure that things come off in time, right? So let's say if you use an isocratic solvent for one run, but the run, like the final molecule, the most polar one on there takes so long to come off, and you get a really broad peak because if it comes off slowly, then your peak will not be sharp, right? So what you might want to do is have a little punch of a more polar solvent come in, which will make it all come off at once, give you a nice big, nice clean, sharp spike on the column, and then it's easier, to integrate and reproduce it. So yes, this will speed up dilution of tighter bound analytes. Sometimes you just don't want to have to deal with it, You don't want to have to wait 40 minutes because if everything else has come off the column and you're just waiting your runtime, you want it to lower. Again, this is like a money thing, right? If you're running an HPLC in a lab, every minute of that running is like probably like $5 do out the window. So you'd rather that happen. So what you would do is if you can add in a little bit of a more polar or less polar mobile phase, then you're able to get it off the column and bring your runtime down to 5 minutes instead of 40. Then you've saved so much time. You can do 100 more runs, during the day. So to review it one more time. So in reversed phase, right? So we have our stationary phase polarity, right? Would be non-polar in reverse phase, polar in normal phase. Our mobile phase polarity would be polar, non-polar, right? And then your analyte elution order would be most polar first, and the normal phase would be most non-polar first. And as you increase the mobile phase polarity, you increase your retention time for reverse phase. And if you increase the polarity for the normal phase, you reduce the retention time. All righty, so I think that's the end of that one. So I wanted to make sure I go into, because your lab teacher was asking me to kind of go over the lab really. Well, I'm not sure if I want to go over the lab, but I would like to go over the lab for you guys. So here we go. So here's our experimental setup. So we have a classical column chromatography, and I'm not sure if you guys are doing the exact same lab, but it's probably very similar, especially if it's just the online one or just the normal one, right? So what you'll generally see is you have your alumina, you have two sand layers, and it looks like it's been flushed with hexane before the lab. So on our list, remember what's hexane on our list? Let's look at our hexane in terms of polarity. I think this is a normal phase we're doing. Hexane is non-polar, um, a very non-polar mobile phase. So it's been flushed with hexane before the experiment. So we're doing green extract of spinach leaves. So we are putting spinach into hexane as a solvent. And when we put the spinach leaves, basically blended in hexane, right, for the most part, right? we put our mixture of our spinach leaves because there's going to be a bunch of different molecules in there that make different pigments. They're going to be, the family of chemicals will be similar, but the pigments will be, chemically similar, but because of the different colors, it means they have a different structure. So they will have slightly different molecular structures and they'll have different polarities. They'll come off the column in different times. So you're going to put that on top of the column. And it looks like we're doing and yeah, I'm not sure if this is exactly what you guys are doing, but I feel like this would be a little too complicated, but I guess we're just trying I'm not sure exactly what your lab procedure is going to be. But based on the molecules you're expecting, you'll get a different order. So it looks like they used 9 different mobile phases. They did a gradient of phases. So they're slowly increasing the polarity. So 2 mils of hexane is first, then hexane and toluene, then toluene by itself, then toluene and dichloromethane, then just dichloromethane, then dichloromethane and ethyl acetate, and just ethyl acetate, then ethyl acetate and methanol, and then ethyl acetate and 1 milliliter of methanol. So as we go down, you guys will happen to see, right? And again, as you're going along, you would just add this as you go. Once one part has gone into the column, you would just add the next layer, right, of your gradient. So we're going to get a nice, and this is what you should expect to see in the lab. You should get a nice orange band coming out first. And again, it depends what the specific mixture is, but you will see similar things like this. You'll see different colors coming off first. Then you'll get a bit of a grayish green, right? Then we get a bit of a yellow. Then you'll see your dark green band start moving down. So yes. So here are the 4 pigments we're going to be expecting here in the spinach leaf. So we have beta carotene, xanthophyll, chlorophyll A, and is there one more? Chlorophyll B. So those are 4 different pigments, I think. So we got the orange, the grayish green, yellow, and dark green. So 4 pigments. And you guys are going to have to examine those molecules, make conclusions regarding their polarities, and use those conclusions to assign the identity of the first and last colored band that eluded in this experiment. So it might be hard to tell in between, but the first and last should be fairly easy to tell. So that's what you guys are going to be doing in the lab. All right, so that's your experiment that will be done this week, at least in week 2. Let me check that again. Yeah, orientation. So week 1. Now I'm not sure what experiment 1, 1, 2, and 1, 3. I'm not sure if it's all going to be happening at once, but I think this is what you guys should expect in the lab on whenever your lab is Wednesday. So you should expect to see this setup in a burette. Then you're going to have your different gradients of mobile phases going on. Then you're going to have your different bands, 1, 2, 3, and 4 coming off the column. And you guys will be asked, right, to figure out who's coming off first. So remember, whoever has the most oxygens will be the most polar. Whoever has the most oxygens and nitrogens, will be the most polar and come off last. Whoever has the least oxygens and the least nitrogens will probably come off first. And it'll go up as you go down. So whoever has the most will come off last. Whoever has the least will come off first. And then in between, you'll have a gradient. So if somebody has a little more than the other, you'll have one or the other coming off first. So it takes a little bit of examination of the molecules. I'm not sure if your lab instructor has given you the pre-lab yet, but that's how it's going to go. So what I want you guys to do is pull up that quiz that I'm going to open for you guys. I'm going to make it open during the lab time or during the lecture time. So 8 to 9:45, I'll make it open. And then I'll post this video as well at the same time so you guys to watch. And then I think that's pretty much all we have to talk about this week. So again, it's a really fast one this week because yeah, just how brief the study material is. So there's module 2, and I'm just making sure I'm following the schedule as Amanda pointed out. Beautiful. All right, so once again, sorry that I wasn't able to be there this week, but I will be there again the rest of the semester at the 8 to 9:45 to work with you guys in class. Okay. If there's any questions, please email me. Again, it's stephan.haynes@senecapolytechnic.ca. If you have any issues with the quiz, let me know. It's not, 100% built in stone that it should happen on Tuesday. If you're having issues, please let me know. We can figure it out together. Okay. Have a lovely week, and I'll see you guys next time.